Hello everyone, welcome back to the fast track revision series of UGC NET Electronic Science. In this video we are going to learn about 3-bit asynchronous counter. Okay, so 3-bit asynchronous counter we are going to see in this video. Okay, if you are first time to my channel, please consider subscribing and don't forget to hit the bell icon to get video notifications from my channel. Right, so we have already seen 2-bit asynchronous counter. So there I have already clearly explained you the operation also. So here we'll have a glance here. Okay, so clock pulse is directly applied to the LSB bit. So this becomes your LSB bit and this becomes your MSB bit. So here the three stage are there because it is 3-bit asynchronous counter. So if you want to write the counter operation, we have to write QC, QB, QA because this is your LSB and this is your MSB bit. Okay, right. So clock pulse is directly applied here. So and you are giving J is equal to K is equal to 1, right? So for every counter, for every flip-flop, J is equal to K is equal to 1. So output of first flip-flop is connected to clock input of the next higher order flip-flop, and the output of the second flip-flop is connected to the clock input of the third, which is the highest order, right? So MSB bit. So that is why all the three flip-flops will not be in on state simultaneously, because so in order to make this flip-flop 1, so it will be the condition should be QA is equal to 1. So in order to make the flip-flop C, that is the third flip-flop, to be in on state, the condition should be QB is equal to 1. So when QB is equal to 1, then only this will be in on state. When QA is equal to 1, then only the second flip-flop will be in on state. Otherwise they will be in off state only. Okay, so they will not be in on state simultaneously. That is why the word asynchronous, they are not synchronized. That is, they are not in on state simultaneously. Okay, right. So clock pulse is directly applied. Okay, so I have already explained you the operation. So initially all the flip-flops are cleared 0 0 0. So clock pulse is directly applied here. So upon the application of first negative clock pulse, it changes from 0 to 1. So now it changes from 0 to 1. Upon the application of next negative clock pulse, 1 is changed to 0 again. And upon the application of third clock pulse, 0 is changed to 1. Fourth clock pulse, 1 is changed to 0. Fifth clock pulse, 0 is changed to 1. Sixth clock pulse, 1 is changed to 0. Seventh clock pulse, 0 is changed to 1. Eighth clock pulse, you'll have 0 here, and so on, right? It continues. So it changes its state because directly applied here. So upon the application of clock pulse, it is going to complement its output, right? So when will be this second flip-flop changing its state? Only when QA is equal to 1, right? QB is equal to, QB is changing its state only when QA is equal to 1. So QB changes its state only when QA is equal to 1. So now see, so here it is 0, so it does not changes its state, so it continues its state 0. Okay, so next we have 1 here. So since QA is equal to 1, it changes its state. So QB changes its state, so it will become 1 here. And here it is again 0. So when it is 0, it does not changes its state. It will be continuing in its previous state only, not 0. So previous state is 1, so it continues its state. And again here 1 is encountered, so it will changes its state, so it will be 0 here. And again 0 is there, so it does not changes its state and continues in its previous state. So previous state is 0 here, so it continues in 0 only. And again 1 is encountered here, so it will be 1 here, changes its state, so 0 is changed to 1. And again 0 is encountered, so it will be in the previous state only, right, for this. And 1 is encountered here, it will be changed to 0. Okay, so that is the case here. Right. So see the fourth case. So QC. What about QC? In order to have this QC, right? So QC to be on, what will happen? So QA has to be driven by B flip-flop has to be driven by QA. Okay, so then this will be in on state, and again QB has to be driven so that QC will be in on state. So in order for QC, that is third flip-flop, to be in on state, the condition is QA is equal to QB is equal to 1. Then only this will be in on state, because the output of this is connected to this, because this should be in on first. In order to drive the third flip-flop, second flip-flop should be in on condition. Yes or no? So second flip-flop will be on when first flip-flop output is 1, that is QA is equal to 1. So first condition is QA should be 1, so that second flip-flop will be in on state, and second flip-flop output should also be 1, so that it drives the third flip-flop, and QC changes its state. So QC changes its state only when QA is equal to QB is equal to 1. Okay, so remember this. When QA is equal to QB is equal to 1. This is very important. This is why I have taken this 3-bit is asynchronous counter, to make you understand this concept. Okay, right. Now see. So QB is equal to QA is equal to 1. It should be there. So here both are not equal to 1. So it continues its state. Both are not equal to 1. It continues its state. Both are not equal to 1, so it continues its state. Both are not equal to 1, it continues its state. Both are not equal to 1, it continues its state. Now here both are equal to 1. QA is equal to QB is equal to 1. So it will change its state. So it will be 1 now. Now again, so both are not equal to 1, it continues its state. So it will continue its previous state. Both are not equal to 1, it continues its previous state. Both are not equal to 1, it continues its previous state. Now both are equal to 1. So it will change its state. So the next state of 1 1 1 will be 0 0 0. So counter again resets. Okay, counter restarts again. Okay, so if you observe here 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1. That means counter counts from 0 to 7. That is 0 to 2 power n minus 1. So n here is 3. So 2 power 3 minus 1. So total number of states will be 8 totally. Okay, so this is how a asynchronous counter works. I hope you have got a complete idea regarding this. Suppose if you have 4 bit, suppose if you have 4 bits like QD, QC, QB, QA. Okay, so what are the conditions? So just we'll have the conditions only. So QA toggles for every, so it will continue 0 1 0 1 0 1. So toggles for every input clock pulse, right? So there is no condition required for QA. QB, so QB changes its state only when QA is equal to 1. QC changes its state only when QA is equal to QB is equal to 1. Both should be 1. And QD changes its state only when QC, QB and QA, all the 3 are equal to 1. Okay, so if you want, you can write that also, that truth table also, you can solve it on your own, right? So if you observe here, if this is your time period T, so what is the time period here? So on and off, so this is on and this is off totally. So it will is taking 2 clock pulses. So here the time period is 2t and frequency will be f by 2. And here the time period is 4t, the frequency is f by 4. And here the time period is 8t and hence the frequency is f by 8. Okay, so to be precise, the output frequency of n-bit asynchronous counter will be equal to f in by 2 power n. So this is very, very important formula. F out is equal to f in by 2 power n. Okay, so I'm telling you about the MSB bit, right? So at the last output, f out means this is the f out and this is your f in. If they ask about intermediate stages, you have to take this f by 2. First output of first stage will be f by 2, output of second stage will be f by 4, output of third stage will be f by 8. If you have 4-bit asynchronous counter, it will be f by 16. Output of the last stage will be f by 16. Okay, so I'll tell you the important concepts of asynchronous counter in my next video. Okay.